Hello everyone, my name is Will Evans and this presentation covers the end of Chapter 6 in the NREL Best Practices for Operation and Maintenance of Photovoltaic and Energy Storage Systems Guide. Section 6 covers a variety of topics centered on system maintenance, degradation, and end of life. Slide 2 covers the agenda for today's presentation. Our evaluation of the Best Practices Guide will be completed in chronological order, starting with Section 6.6 and ending in Section 6.10. The first section we're going to cover today is Section 6.6, which covers preventative and scheduled maintenance. The three main topics from the test that I wanted to highlight today are that implementing a preventative maintenance schedule can maximize the life of your PV and energy storage system. It should be balanced to the cost of the project. And your protocols need to be dependent on the system's size, design, complexity, and environment. On the slide in front of you, I have a few images. The tables were found in Appendix B of the NREL Best Practices Guide. And the two columns that I find most interesting are the interval as well as the service provider columns. You can see a wide range of intervals from conditional intervals for maintenance to annual. And then also you see a wide range of abilities within the service provider. So you have a simple cleaner or mower trimmer in that top table. And then if you look at the bottom right in the final row, you see a master electrician is needed for some of the scheduled maintenance. So I find it interesting to see the wide variety of employees you need in order to execute a properly preventative maintenance schedule. The two images also show instances of preventative maintenance. So the top right image shows a soiling of the PV module, which needs to activate an array cleaning. In the bottom left image shows an instance of a grounding inspection. Section 6.7 covers corrective maintenance. Now, as a recap, corrective maintenance is required to repair damage or replace failed components. So this is unexpected whenever you have a component failure. The operations and maintenance plan should include how to perform corrective maintenance quickly in response to field failures, including how funds may be used from a reserve or line of credit in order to execute the maintenance. Response time and urgency of repair of specified in the operations and maintenance plan should be balanced with cost and the loss of revenue. And finally, faults or conditions that introduce a safety problem should be addressed as soon as possible, even if the recorded revenue is small. The table on the slide is directly pulled out of Appendix C of the Best Practice Guide. This shows a variety of potential services that could arrive in a corrective maintenance scenario. The graph on the bottom of the slide is pulled from the IEA's review of failures of PV module paper. I think it's a powerful graph at showing likely failures of PV modules over time. One of the main failures seen in PV modules is delamination, and an example photo can be seen in the image in the bottom right of the slide. It is important for me to note that while I highlight PV module failures in this slide, anything in the system can fail, so preparation should be completed for all components. Section 6.8 covers PV module degradations as well as energy storage degradation. Historical degradation rates for PV modules vary greatly, but as technology progressed, these rates became more uniform and are often in the order of 0.5% per year. The image on the left is from the NREL Best Practices Guide, and it provides a breakdown of standard degradation rates for different PV module types. One item that I found interesting is that as models degrade, they do so at varying rates. This causes an induced circuit level mismatch loss that should be modeled in simulations. This could cause complications in maintenance. Degradation rates in batteries depend heavily on usage, temperature, and shelf life. The graph on the right of the slide shows the results of an experiment where batteries were tested for their life cycle with and without thermal management, with varying depths of discharge. You can see that thermal management systems with low depth of discharge will prolong your system's life a great deal when compared to the same system without thermal management with a large depth of discharge. The graph was pulled from the NRELs paper Life Prediction Model for Grid-Connected Lithium-Ion Battery Energy Storage Systems. There are many factors that cause system degradation, so each project should have a unique O&M plan to try and get the most out of the system. Section 6.9 covers example work statements. I pulled the work statement from this slide from Appendix E from the Best Practices Guide. The key takeaway from this section is that the contract needs to be thorough and cover all obligations. Each system will be different from a residential to commercial, so each situation should be handled as an individual project. Section 6.10 covers end of performance period. There are four main options for systems at the end of their life. Option 1 is refurbishing the system and extending its life. There are estimates out there that a refurbished system that's been in service for 25 years can make it over 40 years. Option 2 is extending the term of the performance contract, or PPA. This is going to depend on the performance that the system has withheld through its lifetime. Option 3 is selling the system at a fair market value. And option 4 is removing the system and restoring the site to an earlier condition or other use. One thing that I'd like to talk about is recycling at the end of performance period whenever the system is decommissioned. So demonstration projects at Solar World and commercial scale recycling operations at Force Solar have shown that 84% to 90% by weight of PV modules can be recycled. In the slide, the image on the right shows an exploded view of a solar panel in all of the different raw materials that could be broken down and eventually recycled for reuse. There's a great deal of materials within each solar panel that could be reused in different products later in their life. Another item that I'd like to talk about through recycling is the battery systems. It can be expected that batteries will be replaced 2 or more times during the life of a typical PV system. They just don't last as long as the PV modules. Currently, recycling protocols for lead-acid batteries are robust and executed regularly due to the monetary value of the materials in the mature processes. Recycling of lithium-ion batteries is behind when compared to lead-acid batteries, as the monetary value for the materials and labor-intensive recycling process have not gained momentum. Slide 8 provides the references used and the information gathered in this presentation. Thank you for your time, and I hope you found the information useful and engaging.